This podcast is on functional forms in regression analysis. Functional forms is a term we use to describe ways to make nonlinear relationships between dependent and independent variables be linear. I will exemplify this process during the podcast. One of the major regression assumptions is that there is a linear relationship between the dependent and independent variables. If this is not the case, then the estimates for the model are not BLUE, or best linear unbiased estimators. In other words, this is an important regression assumption for us to consider. Otherwise, we cannot trust the analysis. While the Lewis-Beck and Lewis-Beck applied regression monograph states that numerous real relationships have been found empirically to be essentially linear, it is precisely an empirical question as to whether the equation that we are studying displays that linear quality. If it does not visually look linear, then we need to take action. The most popular action among all the options is to linearize the data. The linearization method is called transformation. It is mathematical, and it is equivalent as well, which is to say that nothing changes about the variable other than the units in which we measure it. Most commonly, we address linearity through a scatter plot so that we can visualize the relationship. The graph on the bottom left of the slide shows a nonlinear relationship between a hypothetical x on the horizontal axis and y on the vertical axis. And on the bottom right, we see the same relationship, though the x variable has been converted to base 10 logarithmic units, of which we will speak in more detail momentarily. However, note that the relationship appears to be much more linear after we have made that transformation. Another thing I should add is that transformations for the purposes of linearization and regression analysis take place on the independent variables only, not the dependent variable. Here are a few examples of some typical nonlinear formations that we commonly encounter. Take my cursor and operate it. Of course, this top left drawing is simply a linear relationship between x and y. A typical one that we see is on the bottom left of the screen. And it looks somewhat like a calculus limit function, where the relationship appears to be a straight line, or a relatively straight line up to a point, and it seems to start to flatten out toward a more horizontal line. This is called a logarithmic function, in that the formula that makes the points be linear is a logarithmic one. The logarithm units, as they increase, take in larger and larger ranges of values. For instance, in a base 10 logarithmic function, the log of 10 is 1, the log of 100 is 2, the log of 1,000 is 3, the log of 10,000 is 4, and so on, adding another 0 to the number as the log increases by 1. This serves to straighten out these curvy data, as we'll see with our example. The sample table of countries around the world, measured by gross domestic product per capita, shows what happens when we log measures with a wide range of values. I just randomly went through the alphabet, found countries, and found GDP per capita measures for them, and created the base 10 logarithm of those GDP per capita measures. Ordinary GDP per capita ranges in these data from $4,625 in Armenia to $60,170 in Denmark. But the log base 10 GDP per capita ranges are much narrower, from 3.665 to 4.779. This variance constriction will tend to linearize data. A research example of this is from the late political sociologist Robert Jackman, who spent his career at the University of California at Davis. Professor Jackman used the power of functional forms to test a series of hypotheses about the relationship between economic development and democracy in countries around the world in a frequently cited article entitled "On the Relation of Economic Development to Democratic Performance," published in the American Journal of Political Science in 1973. Cross-national research was one of Professor Jackman's primary interests, and this research study is an excellent example of it. Professor Jackman was primarily interested in testing the linear positive function relationship that Seymour Martin Lipset proposed in his famous American Political Science Review article published in 1959, entitled "Some Social Requisites of Democracy, Economic Development, and Political Legitimacy," which has been cited more than 10,000 times, according to Google Scholar. Lipset stated that the more well-to-do the nation, the more likely it would be to be democratic, due to an increased desire of the populace to gain political voice with the enhanced economic voice that comes with economic development. Now, if I go back a couple of slides, the Lipset article was essentially testing this relationship right here, that development, as it increases, would also increase democracy in a straight upward trend. But there are other potential functional forms to test as well. For instance, it's plausible to imagine that there are limits to the ability of economic development to push democracy in a positive direction. After a certain amount of economic development, the rate of increase in democracy declines, rather like that of a calculus function. Oops. So again, this logarithmic function might capture those diminishing returns very well. Now, it's even possible that having achieved a maximum democracy score at a certain level of economic development, countries could be witness to a democratic decline as wealth increases after that maximum point. So this drawing here may exemplify that particular idea. And we could imagine that coming about as a result of very high concentrations of wealth in very wealthy countries, which could reduce the political voice of the, so to speak, non-1% of the population. So this is a parabolic transformation right here. As socioeconomic development increases to a point, democracy increases, but then after that, the unequal relationships emerge and democracy declines. So that's another functional form that could be tested. Let's go back to the Jackman slide. Professor Jackman thus tested three potential functional forms of the relationship: linear, logarithmic, and parabolic. Now, on this table 1, this first model is simply the linear relationship tested, x sub 1. The second model is the parabolic transformation, which is x sub 1 and x sub 1 squared, which will result in a parabolic transformation. The third model tested is the logarithmic transformation, and that's this x sub 3 right here. Now, if we look at the models themselves, statistically speaking, it appears that model 2 performs the best. So if I can get my cursor back, we look at the R-squared statistics, and we compare them across the three models, and it's highest in model 2, the parabolic transformation, with an R-squared, if we round to 2 decimal places, of 0.35. That's higher than the logarithmic transformation, where the R-squared, again rounding to 2 decimal places, would be 0.32. And in third, that would be the linear hypothesis, with an R-squared of 0.27. However, when we try to assess, well, which functional form is the proper functional form, we have to include not only the statistics, but also the visuals. So this is from Jackman's article. He tested roughly 60 countries measured in the year 1960 in this study. And he has plotted all 60 data points. Kind of hard to see the numbers, but they're there if you want to look up the article itself. There are some subtleties to note, as Professor Jackman is careful to note. For instance, this is one of those models where the y-intercept actually matters. So I'm going to go back to the statistics. Notice the y-intercept is quite different between the linear, parabolic, and logarithmic. So the y-intercept is actually rather high in both the linear and the parabolic. And you can see that the y-intercept with the lines drawn in, this is the linear relationship. This is the logarithmic relationship. And then this dashed line here, that's very curvy, is the parabolic relationship. So certainly true that a lot of the data points hover around this 55, 60 level as the y-axis is encountered when x equals 0, which would be right here. There are a substantial number of data points that are below that 50 mark. And you can see that the logarithmic line actually has an intercept of around 15, which incorporates about a fifth of the total number of data points if you add up these numbers here. So in a sense, the logarithmic transformation is capturing more data than are the linear and the parabolic transformations. It does seem like if we just look at the data points and imagine no lines at all, so imagine that we don't have any dashed lines or solid lines, that there is a kind of a curve here. It looks like that there is a curvilinear as opposed to a linear relationship. The line, the regression line, if it's just simply the linear function that we're looking at, doesn't really hit many of the data points at all. In fact, some of them are quite far from the line. So it doesn't look like the linear estimation is going to be the best one. What about the parabolic transformation, which had the highest R-squared value? One of the reasons that a really high R-squared value is because there's an outlier country out here, and that's the United States, which is not quite the highest in terms of democratic performance, but is easily the highest amongst these 60 countries in terms of economic development, measured by energy consumption per capita. So in a way, this parabolic transformation is taking into account pretty significantly this one outlier. So it might be biased toward the United States and not really capturing very well some of the other variation, especially on this lower end here. And it turns out that Professor Jackman, because the logarithmic transformation takes into account these lesser democratic performing data points and is not as influenced by the outlier of the United States, that the logarithmic transformation is in fact the preferred functional form. So that's the one that is best for him. But it's a matter of interpretation. What we do see is that it is possible to linearize data, and it is possible to choose between several different functional forms. And thus this is a very useful exercise in the functional form application in regression analysis. Now we're going to look at, this is focused on logarithmic versus parabolic. I'm just going to do one more that focuses heavily on the parabolic transformation. And this is from a study that I authored and a journal called the European Journal of Political Research back in 2000. So the dependent variable is the democracy score from a scale called the polity scale, which is often used as a way to measure democracy. And I have a couple of different models here, but I'm particularly interested in the relationship between capitalism and democracy. The measures of capitalism that I am using comes from an organization called Freedom House, which is a democracy tracking organization. And from 1995, I've had 81 countries in my data set. And it looks as if there is a nonlinear relationship between the economic freedom scores and democracy. And in fact, because the economic freedom scores are statistically significant in both of the models, the figures in parentheses are absolute t ratios, it does seem that the parabolic functional form is one that works very well in capturing the relationship between capitalism and democracy. So I'm going to go back up a couple of slides and note this is the parabolic relationship. And I'm hypothesizing that as economic freedom increases beyond a certain point, this inequality takes place and seems to deny the masses' political voice, or restricts it somewhat, and also restricts democracy. So I'm finding evidence for that in my cross-national study, which again is of 81 countries for the year 1995. So again, we have an instance of where variable transformations makes relationships between independent and dependent variables be linear. So that's the point of doing variable transformations. Again, it doesn't make a new variable, it just simply creates a different scale for measurement of variables that are being transformed. So again, this is very important for us in order to make valid blue inferences, best linear unbiased estimator inferences, from the regression model estimate. We must try to make our relationship between the independent variables and the dependent variable be as linear as possible. Okay, so that's, again, a lot of information, and I like to end these information-intensive podcasts with a little bit of serenity to recenter ourselves, if you will. So for this podcast, I've chosen a photo of the Blue Mountains in the area north of Baker City, Oregon. I think many of us who've driven on I-84 have gone through the Blues during winter time over that major pass, the Dead Man Pass, going from approximately La Grande down into Pendleton, a very long pass and kind of a windy pass. Know that it's blues can be a little bit dangerous, certainly in terms of travel, but are very pretty to look at, and I think this is a very serene photo of them off in the distance with agriculture taking place in the foreground in the very rich Baker Valley area of eastern Oregon. So thanks for watching this podcast, and have a nice day.